In this lesson, I'll show you how to write a Maclaurin series for a function. This is question number 1. A Maclaurin series expresses a function, let's say f at x, in terms of an infinite power series whose nth coefficient is the nth derivative of f at x, evaluated at x is equal to 0 and divided by n factorial. The first question reads, write a Maclaurin series for the function f of x is equal to sine x. Take a look at the Maclaurin series. What we have to do is find out what sine at 0 is. That will take care of the first term. Sine at 0 is equal to 0. Next, we have to find out what f prime at 0 is equal to and multiply that by x. Therefore, we have to find the derivative, or the first derivative, of sine x. The derivative of sine x, which I'll represent as f prime at x, is equal to cosine x. And cosine at 0, so f prime at 0 is equal to 1. So as we build our Maclaurin series, we have f at x is equal to 0 plus 1 times x. And then we have to add f double prime at 0 over 2 factorial times x to the power of 2. So we have to find f double prime. Taking the derivative of cosine x, we end up with negative sine x. Evaluating negative sine x at 0, we end up with, once again, 0. So technically, this whole term becomes 0. Now for the next term. It's not shown here, but we know that we'll need to take the third derivative this time. So the third derivative of our second derivative, which was negative sine x, will be negative cosine x. We take negative cosine x and multiply it to x to the power of 3. And we evaluate this at 0. Negative cosine at 0 is equal to negative 1. So we have negative times x to the power of 3 over 3 factorial, which is equal to 3 times 2 times 1, and that's equal to 6. So the next term in our series will be negative x to the power of 3 over 3 factorial. Given what we discovered about the third term, we learned that it goes to 0. So we can assume the same thing will happen when we find the fifth term, the one after this one. So we'll skip the fifth term and move directly on to the sixth. So we'll find the fourth derivative, which will be equal to sine x. We're skipping this one. The fifth derivative will equal to cosine x. This will be multiplied to, unlike in this term, to x to the power of 5, and we'll have 5 factorial at the bottom. Cosine at 0 is equal to 1. So the next term we would have to write is x to the power of 5 over 5 factorial. I'm going to highlight the significant terms that we found, and this would continue, of course. That's the answer to question number 1. Now we'll move on to question number 2. We're asked to find the sine of 0.5 radians using the first 3 terms of the Maclaurin series. We have to work to 7 decimal places. So right here, what I'll do is write down f at 0.5, and that's in radians. And I'll make that equal to, applying 0.5 into this x, we have 0.5 minus 0.5 to the power of 3 over 3 factorial plus 0.5 to the power of 5 factorial. Those are the first 3 terms. Using my calculator, 0.5 minus 0.5 to the power of 3 divided by 3 factorial, which we know is 6. I'll close the bracket. Plus, once again, 0.5 to the power of 5, all divided by 5 factorial. We'll write down 5 and then shift this button. We'll end up with 0.479427. They want it to 7 decimal places. So everything after this 0 is insignificant. This 8, 3, and 3 will be truncated. The reason why this question is being asked is because this number isn't as accurate as you think it would be, even though it's coming from a calculator. Because it turns out that if a computer were to calculate this more accurately, sine at 0.5 radians would be 0.4794255. This means that our answer would be too high by approximately 0.0003%. While this may seem minuscule and small, the error caused by discarding terms of a series is called truncation error. So expect that when you're working with Maclaurin series. Finally, in question number 3, they ask us to write a Maclaurin series for f at x is equal to ln x. What's interesting about this function is that if you evaluate this at 0, it comes out undefined. And in order for us to write a Maclaurin series for a function, the function and its derivative must exist at x is equal to 0. Therefore, we cannot write a Maclaurin series for f at x is equal to ln x. In order to actually do this, you'd have to express it using a Taylor series, and we'll do that in a later video. And so there you have it. 3 examples on how to write a Maclaurin series for a function.